In this review, I'm going to be focusing on electronegativity, its role in understanding the polarity of bonds, and ultimately the idea of hydrophobicity versus hydrophilicity, whether a molecule is soluble in water or not soluble in water. So electronegativity is basically defined as the propensity for an atom to pick up an extra electron. And so here we see the periodic table, and hopefully you remember from chemistry some basics of the periodic table. But essentially what you're looking at is we have all of these elements that are organized into various columns. And those columns really are based on the number of electrons they have in their outer shell. So we can see over here we have the noble gases. Those noble gases have the outer shell filled. Helium, this row here, really only has 2 electrons in the outer shell, and so it has both of its electrons, it's full. The rest of these basically have 8 electrons in their outer shell. What this suggests is that we can figure out exactly how many electrons each column or each element needs to fill its outer shell. And for the most part, we're looking at the rule of 8. In other words, the element wants to have 8 electrons in its outer shell to have it full and therefore be stable. So the elements in this column here basically have a valence of 1 because they need 1 electron in their outer shell to have it full. This column here has a valence of 2. Column here has a valence of 3. Carbon's column has a valence of 4, and so forth. These valence numbers also would basically indicate how many bonds each element is going to make, because in a covalent bond, if you remember, an element is sharing electrons, and it does that in order to try and fill its outer shell. So oxygen is going to make 2 bonds, which is why we have the molecule H2O, because one oxygen is making a bond with 2 separate hydrogen ions, and that suffices for its valence of 2. Now, what does this have to do with electronegativity? Well, basically, the closer an element is to having its outer shell filled, the higher a propensity it has to bind and grab other electrons, and thus its electronegativity is higher. So you can basically see that as you move from left to right in the periodic table, the electronegativity is going to increase. In other words, fluorine has a higher electronegativity than oxygen, and oxygen here would have a higher electronegativity than nitrogen, and so forth. This also works, although to a slightly lesser amount, as we work from the bottom up. So the higher ones have a little bit higher electronegativity than ones directly underneath it. Now for this, I'm mainly going to focus in on the elements that we are concerned about, and that is carbon, nitrogen, oxygen, and then I'm going to bring back hydrogen, which remember was over on the very left column. But hydrogen, along with these other 3 elements, these are the main elements that make up the biological molecules that we are interested in. And so if you look at electronegativity here, the ones that you really need to worry about, we know that oxygen has a higher electronegativity than nitrogen, which has a higher electronegativity than carbon. And the one thing that is a little bit strange you have to think about is hydrogen and carbon basically have a very similar electronegativity. And the reason for this is if you think about it, carbon has a valence of 4. In other words, it needs to add 4 electrons in order for its outer shell to be full with 8. So it's halfway there. It is halfway to having its outer shell filled. Hydrogen only has 1 electron in the outer shell, but its outer shell only has 2 because it's in this column here, or this row, sorry, here with the helium. And that means it also is halfway to having its outer shell filled. So basically you just have to remember that hydrogen, for the sake of biological purposes, hydrogen and carbon have a very similar electronegativity. Now, what does this mean with regards to bonds and polarity? Well, here we have an oxygen atom and 2 hydrogen atoms. And remember, oxygen's valence is 2, which means it needs to add 2 more electrons to fill its outer shell. And so it does that by sharing these electrons in a covalent bond with hydrogen. Now, we know that oxygen's electronegativity is higher than hydrogen's. And if you want a way to remember that, you have to think of hydrogen as having the same electronegativity as carbon. And if you put hydrogen where carbon should be, you can see that in the periodic table, which I don't have up here at the moment, but oxygen is further to the right, therefore it's more electronegative than carbon, and therefore it's also more electronegative than hydrogen. That means that these electrons are not shared equally between oxygen and hydrogen. They're actually pulled a little bit closer to oxygen, and since electrons have a negative charge, this gives oxygen a negative dipole. It's not a full charge, they're not stealing the electrons, but it is a dipole, it's a partial charge. And in doing so, the hydrogens get a partial positive charge. And these are polar bonds, and this is a polar molecule now because you have a slightly positive side and a slightly negative side, and that gives this molecule polarity. On the other hand, any bond, covalent bond where there is no difference in the electronegativity, or very little difference at least, that means that that would be a nonpolar bond. For example, when oxygen fulfills its valence by doing a double bond with another oxygen, both of these have the exact same electronegativity. It'd be like having a tug of war with a clone of yourself. Therefore, there is no propensity for the electrons to move one way or the other, and that would be a nonpolar bond. The other ones to remember are not only carbon versus carbon, so again we have a nonpolar bond because it's the same atom bound to itself, but any carbon bound to hydrogen, remember those two have the same or similar electronegativities, those are also nonpolar bonds. And we know that because water is polar, it likes to interact with other polar things. So this gives us the idea of hydrophilicity. And something is soluble in water if it is polar, and it's non-soluble in water, or hydrophobic, if it's nonpolar. So here we have an example of a triglyceride, which is a nonpolar molecule, and you can tell that because we have all these hydrocarbons here. And this makes sense because we know that fats are not soluble in water, therefore this is hydrophobic. On the other hand, we have the classic structure of a sugar here, and you can see that we have all these polar bonds. We have carbons bound to oxygen, we have oxygen bound to hydrogen, and all of those bonds we know are polar. And there are polar bonds all over the place in this molecule, and therefore this is hydrophilic. It is going to dissolve very well in water, and we know that sugar dissolves well in water. So in summary, polarity is really important. If two atoms are bound together covalently and they have different electronegativities, the one with the higher electronegativity will end up stealing the electrons a little bit and have a negative dipole, and the other element will have the positive dipole. On the other hand, if the bond is between atoms with the same electronegativity, a la hydrocarbons, those are going to be nonpolar.